Everybody, Dr. White here, continuing our discussion of Bayesian estimation. Going to do exercise number 1, where we get introduced to another conjugate pair, the gamma-Poisson pair. So, suppose that there's some unknown parameter that you treat like a random variable, capital theta, and it has the gamma alpha beta distribution. So you get to know alpha and beta, but you don't know what theta turned out to be. And let's say you're going to have some data. You have y1 through yn independent random variables, and you're interested in their sum, capital Y. And each one of these yi's is Poisson with that unknown parameter, theta. So by the way, you'll notice that y itself, being the sum of n independent Poissons, is Poisson in theta. And so given that data, let's say given that capital Y turns out to be little y, could you find the posterior PDF for theta? So Bayes' theorem says you're looking for k of theta given y, and it's going to be the conditional of the data given theta's PMF, because y is a Poisson, it's discrete, times the prior h of theta, PDF, over the unconditional probability that capital Y equals little y found by conditioning on theta. So there it is, that usual integral on the bottom. And so you fill in what you know. Okay, here is the PMF for Poisson at y. Here is the PDF for a gamma alpha beta at theta. And here's the integral filled in. Now, we are going on the hope that the posterior PDF is some familiar distribution. And so what we're going to do is find the parts of it that depend on our variable in the distribution, little theta, and separate out the parts that do not depend on that variable. And so when I look at all of this stuff, I first notice that everything on the bottom does not depend on theta, because you'll have integrated theta out by the time you do that definite integral. As far as the top is concerned, there's a great deal that does not depend on theta, like that stuff or that stuff, but there is some stuff that depends on theta. I see a theta to the y right here. I see a theta to the alpha minus 1 right here, so I'm going to gather that down here. I also see e to a couple of things involving theta, and so I'm going to use property of exponents, gather them together. I'm also factoring out the, I did not want to do that. I'm also factoring out the common theta to get this expression here. So everything else does not depend on theta, so I just call it a number C. Now I do a little bit more work on this power of E. I'm going to write it, I'm going to write the n plus 1 over beta as 1 over its reciprocal. And then when I look at what I've got that depends on theta, I see that's in the form of a gamma random variable. And so I know that it has to be a gamma. There can't be two different PDFs that have that same form. So the posterior is a gamma, where the first parameter is this, the alpha plus y, and the second parameter is this stuff on the bottom that I've rewritten slightly by multiplying top and bottom by beta. So there we go. So, if you wanted to do specific things, like, say you wanted to make a point estimate of what theta is, before you had any data, the point estimate you might have chosen to be the mean of the capital theta prior distribution. And so that would be alpha times beta. On the other hand, if you wanted to pay attention only to your data, what would you do? Well, here's a suggestion for you. The mean of capital Y is in theta, because the mean of a Poisson is its rate. And you get this one value from your capital Y. And so you figure if you grab from a distribution that you might come somewhere around its mean. And so you figure that Y might be approximately n theta. And so you figure theta might be approximately the Y you found divided by n. So that could be a data-only estimate for theta. But of course, what you're going to do is combine the prior knowledge of theta with the data knowledge of theta and use the posterior distribution to get an estimate. So why not do the conditional mean of theta given your data Y? And so that would be the first parameter in the gamma times the second parameter in the gamma. And just like the example that we considered earlier, it turns out that you can express that posterior conditional expectation as a weighted average of the data-only estimate of theta and the prior-only estimate of theta. The weights, this and this, you can see they really are weights because if you add them up, they come to 1. And notice that if your sample size n gets really big so that you have a lot of data stuck together in your sum, then the weight accorded to the prior goes down to 0. And the weight accorded to the data only goes up to 1. This makes sense. The more data you have, the more weight you're going to give to your data as opposed to that old knowledge about the population of possible thetas from which your theta was treated as coming randomly. So here's another example. And sorry, it sounds like there's hammers somewhere in the hallway. We'll just have to live with that the rest of this screencast. Another example, say that x1 through xn is a random sample of size n from some distribution. Call it some underlying distribution, capital X. And let's say that the PDF for this distribution, it depends on a number theta, and its formula is 4 theta x cubed e to the minus theta x to the fourth for all positive real numbers x. Okay, so like each of the xi's would have that distribution. Like a capital Xi's PDF would be 4 theta xi cubed e to the minus theta xi to the fourth. Now, we don't know theta, but suppose we can treat it as a trial of some random variable capital theta whose distribution we do know, and say we know it's gamma alpha beta. Could we get the conditional expectation for theta given data? That is, given that capital X1 turned out to be some specific little x1 all the way up to capital Xn being some specific xn. Could we get that conditional expectation? So you can see that this problem involves a multivariate random variable. Instead of just a bivariate random variable, theta, comma, y as your data, here it's theta, comma, x1 through xn in data pieces. These n data pieces aren't being combined into one piece of data like we did in the previous example. So we're sticking with a kind of multivariate situation here, but that doesn't really make the problem any more difficult. We'll see why. We still want to determine the posterior PDF for theta conditioned on the x1 through the xn. Then we can just take the expectation, we can get an expectation out of that. So that's still our goal. We write it a little bit differently because of the multivariate situation. K of theta given little x1 through xn equals the conditional multivariate distribution of the x1 through the xn given theta. And so this is going to be the joint PDF for the multivariate random variable x1 through xn, given that capital theta worked out to be little theta, times the prior on theta, times the unconditional probability or density that capital X1 turns out to be little x1 all the way up to capital Xn turns out to be little xn. Unconditional because we've used conditioning to integrate out. So same formula as before, and so we just fill in what we know. Now, it's very helpful that the x1 through the xn are independent of each other, because a joint PDF, when the variables are independent, is going to factor as the marginal PDFs for the variables separately. And so that's what we got here when we write in for it. We got the product of the marginal PDFs for each of those xi's. And capital theta was a gamma alpha beta, so there's the PDF for the little theta. And we got this integral down here, which I didn't really have to change at all. I just wrote in that the sample space for capital theta was 0 to infinity up here in front. That's about all it did, but I didn't even need to do that, because I am still going on a hope that maybe the posterior PDF for theta is some familiar PDF. And so I just got to get its basic form by separating out the stuff that depends on theta from the stuff that does not. So I go through that process again. Once again, the bottom, it's not going to depend on your theta. From the top, I see here's a theta that's getting multiplied by itself n times. So I've got to write that in there. There's also this, and so that's e to the minus theta x1 to the fourth times e to the minus theta x2 to the fourth, and so on. So when I use a property of exponents to put those together, that's e to the minus theta times a sum. I goes from 1n xi to the fourth. Okay. Where do I see some other thetas? Yes, there's one here, so I made sure to get it written down, and one here. Okay, and nothing else depends on theta. I call everything else a c. And I combine as best I can. I see that there's n plus alpha minus 1 thetas. There's a couple of exponents with base e, and I put them together with property of exponentials. And so I would have an e to the minus theta this plus a 1 over b, and I'm going to write that as 1 over its reciprocal because I want to be looking at the form for a gamma. This is another gamma. So we got another conjugate pair up here. You know, this kind of mystery prior with this gamma prior with this mystery data variable, this interesting distribution here, also turned out to be a conjugate pair. So the posterior PDF is the gamma with, oops, and there's a typo there. That should be an n plus alpha, not an n plus alpha minus 1, an n plus alpha, arg. And then here's our second parameter. So the conditional expected value would be the alpha, which is just n plus alpha, times the other parameter, so 1 over this stuff. And so n plus alpha divided by this stuff. And I don't know if that's particularly pretty or worth simplifying any further. The main thing is, hey, easy to get another conjugate pair this time. Now, fact is that conjugate pairs are rare in Bayesian estimation. And another thing is that, you know, when you can't get a familiar distribution for your posterior, you know, when you can't get that to come down to a familiar distribution, then you're just going to have to evaluate it to get the posterior PDF, which means you're going to have to do a nasty integral down here, you know. And so in real life, Bayesians had to think about how to approximate integrals that couldn't be done analytically. And that can be very difficult, especially in multivariate situations. So, well, this one here is not multivariate. If the sometimes the prior parameter itself is multivariate, and you have a multivariate integral that you got to do, and so that could be very difficult. And so Bayesian analysis was actually held back for a long time until computers got more powerful and these approximation routines got better. I'm going to do an example here to kind of close things off. It's not a straight up Bayes theorem, but it is a situation where you're going to find some kind of posterior probability, as a conditional probability, just to show you how often you end up working with data to make some guesses about something. So I call this the problem of the exponential bank tellers. Say you're a customer at a bank, and that bank has a lot of tellers that work at the bank. And each teller, when he or she gets a customer, takes a random amount of time to process that customer's request. And the time that he or she takes is exponential with the parameter theta, mean theta, where each teller has his or her own value of theta. Each teller has his or her own average time, okay? But if you could put all of those tellers' thetas together and make a graph of them, it would look uniform, where the lower bound of theta is 2 minutes and an upper bound of theta is 50 minutes. So you can think of it as each teller, if you grab a teller at random, that teller is equally likely to take an average of 2 to 50, anywhere from 2 to 50 minutes to do a request. So say you pull up to the bank, okay, and a random teller is going to help you. What's the probability that your transaction is going to require more than W minutes? Can we find that probability as a function of W? Well, why don't we let capital T be the time that your transaction takes? That's a random variable. We're looking for the probability that capital T is bigger than W. Now, I think we could figure out the chance of waiting more than W minutes if we knew the teller's theta. I think we could find this probability right here, okay? Because that's the chance that an exponential is more than W, and the chance that an exponential is more than W is e to the minus W over the theta parameter for the exponential. So let's leverage that to do conditioning to find this probability. This probability should be the sum of the probability of this times the chance that theta is equal to exactly that little theta. Well, here theta is a continuous random variable, so there's the probability that capital theta turns into a particular little theta is always 0, but we do have the density. The density there, 1 over 48 times d theta, is the probability that capital theta turns out real near theta. And then we could just take that sum over all the possible little thetas, and we've done our conditioning formula to find this probability. So this it's just same kind of conditioning that we did way back in chapter 1. It's just now that the variable we're conditioning on is continuous instead of discrete, and so we're doing integral of the conditional thing PDF rather than sum of the conditional thing probability. So looks real promising, but then when we look at the integral itself, we realize, oh boy, that's a function of theta, and I don't think I can get the antiderivative for that thing. So to get this definite integral, we're probably going to have to use approximations, like you learned in Calc 1, like Simpson's rule, things like that. we'd probably better get a computer to help us with that. So let's head to R and see if R can help us out. So here I am in R, and let me go to the common folder, Dr. White stuff, Math 331, and under scripts, there is a section 6.8.R. We've worked through some of this in an earlier screencast, but let's now do the part on the bank tellers. So here's just a reminder of the situation we're in. And now here's that question we face. Random teller is going to serve you. What's the chance you have to wait more than 5 minutes? And we've got to figure out a way to get this definite integral back here. Okay. Now, so we're going to have to integrate this thing. Okay. Now, this thing is a function of theta, but you actually have a different function for each different w. Okay. And I would like to be able to answer this question for different values of w. So I'm actually going to need to make any function of theta that I want for any w. So how can I make R do that for me easily? I've got right here, I'm constructing a function that I'm going to call fmaker, and it is a function of a variable w. And inside the braces here that start here and end here, all it does is construct a function of theta, which is 1 over 48 times e to the minus w over theta. So this is a function. Fmaker is a function where you give it a number and it will return a function. For example, fmaker of 5 is going to give you a function where the w is 5. It's going to give you the function 1 over 48 e to the minus 5 over theta. So let's go ahead and run the fmaker of 5, and its result we'll call f5. It'll be in the global environment there. Oops, I need to first of all get fmaker in the global environment, and then I can use fmaker, and I've got my function of theta over here in the global environment. So for example, 1 over 48 times e to the minus 5 over 11 would be f5 at 11. The 11 is the theta value. That's pretty small. It's about 0.013. Now what I'm going to do is just show you what that integrand of this, I'm going to show you what the integrand of this definite integral looks like. So here's the integrand. I'm going to show you a graph of that where the w is 5. So I'm going to show you a graph of that f5 function we just made. So to make that graph, I'm going to make a little data frame here, which has 2 columns, a theta column, and it's all the real numbers from 2 to 50 going up by 0.01. So just a whole bunch of those whole bunch of values from 2 to 50. And the second column is f5 applied to each of those values. So I'll make it, and I'll just take a quick look at it. So for example, when theta is 2.01, e to the minus 5 over 2.01 is this little number here. That's what this data frame is telling us. Next, I make sure I've got ggplot2 attached. And then I make a little line graph. It's going to just plot all of these points where on the x-axis we got the theta value, and on the y-axis we got the f value. and it's going to connect those points with lines. So it's going to have a pretty good idea of what the graph of the integrand is. And so if I move my face, you can see that graph. And we've got to take the area underneath this graph from 2 all the way to 50. Got to find that area. Okay, that's what that definite integral here is. All right. So what do? How do you do a definite integral in R? Well, there is a function called integrate. And what you do is you give it the function that you want to integrate. And so that's that f5 function here, which I'm calling f maker of 5, gives you that same f5. Could have just written f5 in there. And you got to say the lower bound where you're integrating from, the upper bound is where you're integrating to for your integral. So this number that's about to come out will be the chance that you have to wait more than 5 minutes. Ready, set, go. 0.75 roughly, with absolute error 6 times 10 to the negative 8. And so it's saying that that definite integral came out to be about 0.75, and the approximation technique it used, it thinks it has an error of less than 6 divided by 100 million. So pretty small error. And so we're pretty sure that the probability of waiting more than 5 minutes is about 75%. Okay. I would like to save that number for future use. So kind of makes sense that you might set up a name, how about more than 5, and bind to that name that number, which is the result of doing that process right there. So let's go ahead and run line 73 here. And you get more than 5 in your global environment over here. And I'm a little suspicious because instead of just saying a 0.75 over in this second column gives the values, it says list of 5. Maybe I should push the little blue button here and see what this list is. Oh, it's like a list giving you all kinds of information about the routine and how it ran and what things went well and didn't go well. And it's just really that first item in the list that you want, the value item. And so, like, how could you just isolate that one thing? Well, when you got a list in R, if you can isolate things in the list by using a $sign. So I got my name of my list, which is more than 5, got my $sign, and then I got the name of the item, value. So like if I just run line 74, that gives me the number. Okay, so I just need to remember that. Now, I want to take this a little further. Say that a random teller starts helping you with your request. And before she started helping you, you were thinking, I've got about 75% chance to have to wait more than 5 minutes. So you're kind of expecting that'll happen. And say 5 minutes pass and, you're still not done. What's the chance that you're going to have to wait more than an additional 5 minutes? Now you might say, hey, exponential random variables, they're memoryless, and she's running on an a trial of an exponential random variable. So the chance for her to take 5 more minutes should be the same as the chance for her to take 5 minutes, to take more than 5 minutes right from the start, right? And so it'd be very tempting to say 75%. But 75% is the chance that you've got to wait more than 5 minutes before you even start, before you even get a teller assigned to you. You're in a different situation now. You've got a teller assigned to you. There's not a range of theta values out there. There's one particular theta value out there, and the chance for that teller to take an additional 5 minutes is not the same as this kind of weighted chance that we computed for the tellers to take more than 5 minutes. So we have to think about this differently. So, well, let's see. I do know the unconditional chance that you, or I know how to find the unconditional chance that you would have to wait more than 10 minutes total. So that's the 5 you've already waited plus another 5, okay? That would be just this, where the W is a 10, okay? So it would be this integral where the W is a 10. Can we at least find that chance? The chance of waiting more than 10 would be this value. And so I'm going to store it as more than 10. Ready? Run line 81. So there's more than 10. And when I click on it, I see a 0.598. Okay, so there's a 59.8% chance that you'd have to wait more than 10 minutes. So like, this means like at the beginning, before you're assigned a teller, you're wondering, what's the chance I got to wait more than 10 minutes? 59.8%. Now we got to find the chance that you wait more than 10 minutes, given that you've already waited more than 5 minutes. So we think that's conditional probability. Probability of A and B divided by probability of B. All right, think about probability you got to wait more than 10 and wait more than 5. Well, that's the same as that you got to wait more than 10. And then you divide by the probability of the B, probability that you wait more than 5. So you're taking yourself back to the time 0 before you're assigned a teller. You get your probability of A and B. Taking yourself back, you get your probability of your B. And that ratio is what you want. So I'm going to compute it here. So it's about, given that you've been waiting more than 5 minutes, there's about a 79.5% chance you have to wait more than another 5. This kind of makes sense. Since you've been waiting a while, it's now less likely that you got one of those tellers with a very small theta time, you know? And so the tellers you're more likely to have gotten are the ones with bigger times. And so there should be a bigger chance of having to wait 5 more minutes. Makes sense. Next one down the pike here. What if you wait another 25 minutes? So you've waited like 30 minutes by now, and the teller is still not finished. What's the chance you're going to have to wait more than an additional 5 minutes? Well, this is going to be pretty easy. Chance of waiting more than an additional 5 minutes would be a chance of waiting more than 35 total. But we got to find the probability of that, given that you've already waited the 5 plus the additional 25, given that you've already waited more than 30 total. So I've got to find this quantity. So I need my more than 30, I need my more than 35, and then I'm ready for my conditional probability. It's like 85%. And again, that continues to make sense. If you have waited 30 minutes so far, well, it's kind of unlikely that you had some of those tellers with like the really low thetas around 2, 3, 4 minutes or so. For those tellers, it would have been unlikely for them to take you so long. And so most likely you've got tellers with larger thetas, and so we get this larger result. Same idea here, except what if you've been waiting for 1,000 minutes? So again, I would just get the probability of 1,005 divided by the probability of 1,000. So let's just see what that's coming to. About 90%. And you can imagine, you know, the probability will get higher and higher the longer you wait, but it won't converge to 1, but it will get higher and higher. So This is just an idea that you can still use the conditional probability approach, even in situations where you don't have to, where what you know does not require you to go and find the full posterior PDF, which can often be numerically difficult in Bayesian situation to find. Well, that's all I got for today. See you another time.